We continue the projectile motion in this second video. In the first video, we started by explaining the concept of projectile and projectile motion. And then we defined some terms and we started the analysis. And then in that same first video, I did say that the initial speed of projection is my u and is projected at an angle theta degrees to the horizontal. The theta is the launch angle or the angle of projection. And I said after some time t seconds later, the projectile is at point A, and that we can resolve that this projectile at point A has some components, that is two components of the velocity. We have the Vx, which is acting horizontally, and the Vy, which acts vertically. And I said that this Vx is always constant and remains u cos theta, that the horizontal component of the projectile's velocity some time t seconds later is always u cos theta, because the gravity, installation to gravity does not affect the horizontal motion. And then we said vertically that the vertical velocity is affected by the force of gravity, and therefore the body accelerates. If it is moving upward, that's the acceleration. When it's moving downward, that is the acceleration. For instance, if the body is somewhere here, let's call this point C, the body's vertical direction is in this direction, vertical velocity in this direction, downward direction. So which means this time around it increases when it passes point P. The vertical velocity starts increasing. And then we wrote down two equations, one for Vy, we say it is u sine theta minus gt, and then for Vx, which is just u cos theta. In exam situation, how do we use these two equations? The equation will say calculate a body is launched, is projected at angle, let's say 30 degrees to the horizontal. Calculate the projectile's vertical velocity, the vertical component of the velocity sometime t seconds later, maybe 1 second later, maybe 1.5 seconds later. Calculate its vertical velocity, or find or determine its horizontal velocity 1.5 seconds later. This is when we use this equation. We don't use it to calculate the time of height directly, that is to say the time of a flight directly, or the time taken to reach maximum height, or the maximum speed, or what have you. It is used to calculate the speed after some time must have elapsed from when the body was launched or projected. And we continue from there in this part 2, in this second video. We are still going to look at in terms of displacement. This projectile was here before. This is a plane of projection. At point A, you can see that the body has risen. The projectile, let's say it has risen a vertical distance y, and it has also moved a horizontal distance x when it is at point A. Now, what's the expression? We want to write equations or derive equations for y, the vertical distance risen by the projectile, and the horizontal distance moved when the projectile is at point A. So from the second equation of motion, I have s equals ut plus half at squared. So this s becomes the y, equals this will be my uy times t, minus a now is minus g, because since I've taken the upward direction as positive, initial velocity that is acting upward is taken as positive, g must act as negative here, half times gt squared. Now this my uy, recall what we said in the last video, that uy is u sine theta times t minus half gt squared. So my y equals ut sine theta minus half gt squared. Call this equation 3. Now this equation 3 is used to calculate at any point in time the vertical distance risen by the projectile after some given time. Though we can also use to derive the maximum height risen by the projectile. The same equation can be used. Okay, so that's for the vertical distance. Then for the horizontal distance x, we can still use the same second equation of motion, u times t plus half at squared. Here, as I said before, the acceleration is 0. The body moves with a constant velocity horizontally. So it has a constant horizontal velocity. Its acceleration is taken as 0. So this my x becomes x equals this my u becomes ux times t. So that this gives me x equals u cos theta multiplied by t, or I can write it as u times t cos theta. I can call this equation 4. So that is the equation we can use now to calculate the horizontal distance covered. This one is not, though they can be used to calculate the range attained by the projectile. Remember, the range is the maximum horizontal distance, covered by the projectile. But this x is less than the range. So given a time, maybe 2 seconds later, 3 seconds later, and the body is at point A, what is the horizontal distance covered? That's when we invite this equation to calculate such. Now let's say after some more time, the ball or the particle, the projectile is at point P. That's the highest point on its trajectory. We can see the distance from point P, the highest point it reached, to the plane of projection. We call that distance the maximum height attained by the projectile. Recall, maximum height is defined as the highest point, distance from the highest point on the path, on the curve, on the trajectory of the projectile to the plane of projection. That is the maximum height attained by the body. Now, at point P, what happens to the projectile at P? At its highest point, we should know that the vertical component of the projectile's velocity is always taken to be zero, or is zero actually, because it has reached its highest point. This is the case. It's like the case when a body is projected vertically upwards. We said at maximum height of its motion, the body is, its final velocity is zero. So similar thing applies here. At point P is highest point on a path of projection, its vertical velocity is zero. I need to also know that it's not just that the horizontal velocity Vx is not zero. Please take note of that. At its maximum height here, Vx is not zero. Vx remains u cos theta. No matter that Vx is constant along the path. Every point on this trajectory, Vx is the same. And the same point P, Vy is equal to zero. So Vx remains u cos theta. Now, let's first of all define the time taken. What is the time taken? Number one, time taken for the projectile to reach its maximum height. Time taken for the projectile to reach, it's not maximum height now. Time taken for it to reach its maximum height. Let's call that time t. How do we prove or find the equation, derive the equation for calculating the time taken for the projectile to reach its maximum height? Now, you need to recall the first equation of motion, or equation for Vy, which is Vy equals u sine theta minus gt. We're going to use this equation. This was our equation 1. So let's recall equation 1. And then also note that at maximum height, the Vy component, that is to say, the vertical component to the projectile's velocity, is taken as 0. So I'm going to replace or substitute 0 for Vy. That gives me 0 equals u sine theta minus g times t. So that if I bring u sine theta to the other side of the equation, it gives me minus u sine theta equals minus gt. So negative cancel negative. So I'm dividing both sides by g. The time of flight t becomes u sine theta divided by g. I'll call this equation 5. Okay, so that's the equation for calculating the time taken for the projectile to reach its maximum height. That's time taken to go from the point of projection to the end of projection. Then let's look at number 2, the time of flight. The time of flight, we use a symbol, capital T, to denote, to differentiate it, distinguish it from the time taken for the projectile to reach its maximum height. The time of flight is the total time taken for the projectile to go from the launch plane to the end of projection, to its final destination. So it can also be seen as the total time the projectile spent in the air, in space, from when it is projected to the end of projection. And this point is always the same plane. This point is at the same plane as the plane of projection. That's the time of flight. And we can see that the time taken for a projectile to go from point O, which is the point of projection, to point P, is the same as the time taken for the same projectile to go from point P to Q. So if it takes time t to move from point O to point P, it's also going to take the same time t to travel for the projectile to go from P to Q, meaning that the total time spent by the ball, which is also the time of flight, is given as 2 times the time taken for the projectile to reach its maximum height. So we can write this as substituting for t. We have the time of flight is 2 times u sin theta divided by g. You can call this equation 6. So the next video we'll look at the other 2 equations for calculating the maximum height and the range of the projectile.